So we're going to do 4 examples. In case you're wondering kind of like what this lecture is going to look like, we're going to talk about theory for about half of it, and then we're only going to do 4 example questions for what it's worth. But before we get to those example questions, we have to make sure we're all on the same page. Okay. So the first piece of vocabulary we need to make sure we're all working together with is the word system. You've probably heard this word system before because we use it all the time in everyday life. I pulled this definition here out of a textbook. Very, very broad, very non-specific. It says a system is 2 or more objects that interact with each other. That could mean almost anything then. Right? When you think of a system, we sometimes talk about systems in biology. For example, your cardiovascular system or your nervous system. That's a type of system, right? There's computer systems, right? Where a monitor and a CPU and a user all interface with each other. Hey guys, can you stop your conversation? Thanks. Okay. In physics, though, when we talk about a system, we're basically narrowing down the universe. If you want to read the second paragraph here, in physics, we can talk about things from the tiniest of electrons to literally the entire universe. And we basically need to figure out what do we really care about, right? And so as a basic example, if I were to, what can I throw here? If I were to throw my keys up in the air, do I really care that a car drove on the street? Does that really affect the keys being thrown the car way over there? Does the fact that as I threw my keys that a volcano just erupted in the Philippines, did that actually affect things? Yeah, I don't really, yeah. So when it comes to describing a system in physics, literally we're just putting a pretend boundary. Sometimes it's pretend, sometimes it's actually like a tangible boundary. But we're trying to designate what do we want to look at. Because we can't look at everything. Is that fair? I can't study my keys flying through the air while also talking about Neptune flying through space. We kind of got to like narrow it down. So it's fairly arbitrary. And you probably know these 3 terms. Maybe you do, maybe you don't. There's 3 main types of systems. There's either open, closed, or isolated. Okay. An open system is a system in which matter is allowed to move in and out. Now, it's not just that matter is allowed to move in and out, but matter actually does move in and out. As I threw my keys in the air, did the amount of matter in the keys change as they moved? And I would say, well, no, not really, right? But this beaker right here, this beaker maybe is a bit of a different system. If this is water, water is slowly but surely evaporating. Does that make sense? And so clearly water is leaving this test tube if that's water right there. So if you have a scenario in which your mass could either increase or decrease, if actual size and amount of what is there could change, it's an open system. Okay. A closed system means basically put a lid on it. As soon as you cap the system, can the water evaporate into the air? Well, no, not anymore, right? It's going to stay inside of the test tube. So therefore, the test tube is a closed system. But it still allows for the transfer of energy. What is physics again? Physics is the study about how matter and energy interact between each other, how energy causes matter to move. Energy can still come and go within the system because like we can still heat this test tube up. We can still make it hotter. Does that make sense? We could add heat. We could add light. We could throw a magnet around it. I don't know what that would do, but we could add magnetic energy. Is that fair? Right. So that's a closed system. An isolated system is kind of like an insulated system. You somehow find a way to make it so that not even energy can get in or out. But the truth is that isolated systems are really hard to achieve. I have a little note down here that says, we normally assume that most systems are isolated, but usually they're not. I can only think of 2 examples in all of physics that I teach to you guys where you'd actually have a truly isolated system. Scenario 1, you work in a vacuum. Anybody know what a vacuum is? What's a vacuum? Go ahead. Yeah.
It's usually a chamber with nothing inside of it, no air.
That's the key. Yeah, like you've sucked all the air basically out, right? And so if you suck all the air out of a system, then as objects are moving around inside, there's no more friction basically. And if there's no more friction, you don't have any way of losing, finger quotes here, but losing energy due to resistance, right? That'd be one example. The other example I can think of is if you work with microscopic materials, and we're talking so small that we're talking like the quantum level physics, like electrons. Electrons are so small that they really can't lose their energy due to friction because they're smaller than the air itself. What is air? Oxygen, nitrogen, carbon dioxide. Well, all of those things are made up of protons, neutrons, and many electrons. If you were to talk about like a single electron moving through a circuit, it's so small, that one electron, that it probably could be considered an isolated system because it is not going to undergo friction because it's smaller than friction is possible at. Does that make sense? So it is possible to have isolated systems, but most of the time they're probably not. Here's another diagram that kind of helps illustrate the main concept. Isolated is literally everything is closed off. No energy loss or gain is possible. Closed, yeah, sure, stuff can go in and out. Open, anything can go in and out. Not only your stuff, but your energy as well. And this is another picture that kind of illustrates the same concept. If I were to build some sort of sealed container to the point that even the sun's rays can't penetrate, it's isolated. But if you have like a beaker that's just sitting wide open here, a baseball could come in, splash this, I don't know how, but apparently it does, and all of a sudden now water spilled out to the outside. Okay. So why do we care? Go to the slide right here. Why do we care? Well, it's all about this physics principle that I want to teach you today called the law of conservation of energy. Scientists have proven over and over again, as well as come up with this theory that makes logical sense. The theory is that our universe has a certain amount of energy, no more, no less. Okay? Our universe, when it exploded into existence and began to go into motion doing all the things that it does, there is this much energy. And we conserve it, because really, if we didn't conserve it, one of two things would happen. Either the amount of energy that we have would slowly but surely drop, which means that our universe would like die out. Or if we gained more and more and more energy, it means things would become more and more in motion, and the universe would keep expanding for forever. And we don't seem to see that happening. We don't think that will happen, at least. So there are some theories about dark energy, by the way, that I don't want to get into right now. But in general, we like to think that there is a conservation law for energy that says what you start with is all there is. And maybe you've heard this term before. It's actually known as the first law of thermodynamics. We teach this in Science 10 in theory. The first law of thermodynamics is very technical. I'll read this here and then I'll put it into people words. But we say the first law of thermodynamics is the total energy in an isolated system is constant. Energy can be transformed, but you cannot create it or destroy it. Meaning, if I go back up here, you can totally turn chemical energy to kinetic energy. You can totally turn that kinetic energy to thermal energy as long as you have, like, say, 100% conversion. If I were to put an arrow on top of this and say that all 100% converted, and as long as that energy remains inside my box, you have an isolated system. But if some energy leaks to the outside, however it does that, then it's no longer isolated. What form of energy is the most likely to leak outside of your system? Heat, thermal, yeah, thermal. Right. And so the truth is that most systems are not isolated, because if there is any amount of heat that can somehow escape, this really is no longer true. As an example, if I were to, say, consider myself a system, and I were to go outside into the cold right now, will the amount of energy that I have remain constant? Well, no. If I go outside into the cold, my heat will leave my body and I'll start to shiver and feel cold, right? Now, I could dress up and I could wear long johns and I could wear 3 pairs of mittens and a toque and 4 sweaters. But if I were to go outside, I would slowly but surely lose my thermal energy to the surroundings. Does that make sense? So, or suffocate, yeah. So, like I said back on this slide back here, we're going to, though, assume that most systems are isolated systems. We're going to assume that we don't lose a significant amount of energy when we do these calculations. That being said, we need to recognize that that's probably not true, because there's friction, there's air resistance, there's heat just being, finger quotes here, but being lost. Now, in the grand scheme of things, is energy ever really lost? Not really. It's just energy is no longer inside my system. It's now outside of my system, wherever I arbitrarily determine it to be. Okay, so that's 10 minutes of me talking about systems, which may seem silly and pointless, but the real key, though, is that if we're going to use this law of conservation of energy, we have to understand that it really is only true if you actually do have an isolated system. Okay? So most of the calculations we do today will only be rough estimates, because of the fact that we don't have the ability to account for that lost energy. Okay. By the way, it's actually physics principle number 5. I can't count apparently. So I've got one more slide, and then we're going to do 4 examples. That will kind of be problem-solving scenarios in which being able to keep track of energy in a system is the goal. Okay? The word we then use, though, to describe all of this energy, we call it mechanical energy. Okay? It's a term used to refer to the collective sums of all types of energy. And for us in Physics 20, that means we're only going to focus on 3 things. We're going to focus on kinetic energy, which has the formula 1/2 mv squared. We're going to focus on potential energy, which could be the formula mgh, or we also learned probably a new formula. It was the formula 1/2 kx squared. You guys recall that one from 2 weeks ago? The k is the like stretchy, springy constant of something that can compress, and x is how far you stretch it. And so this was elastical energy. If you were to add up all of these energies together, we would call that mechanical energy. We usually write it with EM. Now, in theory, we should also be adding light. We should also be adding sound. We should also be adding heat, etc. Does that make sense? But for our purposes in Physics 20, we don't really have a good way of calculating those yet. So we're really just going to focus on these 3 and recognize that these existed, though. Is that fair? So you might be saying, Chris, why do we bother doing all of this? Well, we can make a pretty good estimate, though. So, and like I said before here, as long as the system is isolated, then mechanical energy should be conserved. So here's my goal now. We're going to do 4 examples. We're going to start with like a kind of a low challenge level, and we're going to work our way to more and more challenging. And what you're probably going to find frustrating about this is that when we solve these problems, we don't have like a consistent formula that you say, well, always do this, then do this, then do this. When you're doing physics and you have to use your problem-solving skills, sometimes you have to read between the lines. You have to make inferences. You have to interpret what's happening. And it's not just quite so simple as take a formula, plug numbers into the formula, and ta-da, I'm done. Because that's not really what physics is. That makes sense. So let's try an example. I call these build your own formula scenarios, where we're going to use formulas off your data sheet, but we're going to try to put them together and mesh them together based on the scenario. So here's a scenario. We got a person sitting in a toboggan on top of a 23-meter hill. So I'm going to draw a big picture here. Here is a hill. Wasn't a very good triangle. Here is a person sitting on a toboggan. Is that a toboggan? And they're at the top of the hill. And if you read through this blurb, you might notice that I've only given you literally one number, how high the hill is. And it says that we don't even know how heavy the person in the toboggan are. But the question is, when this person then, slides down the hill, and the person is now in their toboggan down here, as they slide down the hill, the question is how fast are they traveling at the bottom here, which means we're really looking for their velocity. If a lot of times when students are new to working at physics, they'll ask me the question, Chris, what formula do I need? If you could just tell me which formula on the data sheet to use, I can solve the question. But the challenge here is that there's no one formula we're going to use. We're going to use the physics principle of conservation of energy and consider what sort of energy does this person have at the top of the hill. And then we're going to make the assumption that whatever energy they have at the top of the hill, it should 100% still be there at the bottom. Will it, though? What energy will have been lost for sure as the person goes down the hill? Yeah, friction due to heat. Yeah, for sure, right? As the sled rubs against the ice here, there's going to be some. Now, it says assuming no friction, but let's be honest. Is there actually going to be friction still? So here's how I'd go about solving this question then. Let's consider what sort of energies this person has at the top of the hill. And for our purposes, we're only going to do 3. Go ahead. Yeah. No, and that's another challenge, is that in physics, sometimes we have to read between the lines and go, well, what if they are getting a push, right? In lieu of me being toldless, let's start with kinetic energy. Let's assume that they start with no kinetic energy. Let's assume there is no push. Because if there was a push, that would change things. Does that make sense? So let's assume that there is no kinetic energy at the top of the hill. They're basically just sitting there waiting to slide. what about the elastic? Can I go ES for a spring? Are there any springs going on over here? Okay, so no. So what's the only form of energy that they do have? Yeah, they have potential. Yeah, so they have potential energy up here. Now, assuming that 100% conversion rate, which again we already recognize isn't even true, but assuming, then what sort of energies do they have at the bottom? Well, going through that same process, were there any springs going on? No. Do they have any energy left due to gravity at the bottom of the hill? Well, no, because they've used it all up. Their gravitational energy is going down, right? Their gravitational energy is decreasing. What's the only thing left then? Kinetic. It must have gone up, so they must have some 1/2 mv squared. So when I start to build an equation like this, what I would kind of say is that whatever energy that you begin with before you start, should in theory 100% transfer into all the energy you have after you're done. In theory, right? What energy did we have before? Well, we had kinetic, 1/2 mv squared. And ideally, that should completely have turned into mgh, ideally. But rather than drawing an arrow, normally when we try to do physics, we don't draw an arrow, we write an equals sign instead. Right? An equal sign implies 100% efficiency, which is the one thing I'm telling you we don't even have in the first place. But rather than draw an arrow, let's draw an equal sign. And now I have built a formula. And what sometimes kids get frustrated with is that every formula is slightly different. Said that I have these backwards, don't I? I do. You're all just too polite to tell me. Thank you. Hang on. I can't even cut them in half. Okay, hang on. So this one should go there. And this one would go here. Okay. Is that good now? Harrison posited a scenario where what if you get a push? Well, if you got a push, then before you began, you had some kinetic energy because someone gave you a velocity to start with, right? And this is what makes it frustrating to students is that every scenario is slightly different. So I can't give you a hard and fast rule and say always do this in this order. It really depends on the puzzle. And as the puzzles get harder in complexity, you need to draw on other skills. So that being said, for right now, this one is fairly straightforward. Your potential energy will turn into kinetic. Okay. Now let's go a little faster here. What are we trying to solve for? It said determine how fast. Okay, so velocity. So let's now use those algebra skills and solve for velocity. How do I isolate for v right here? Just talking through. You have to get rid of a 1/2. So times by 2. How do you get rid of the m? Divide both sides by m. And you know what's really cool about this? Is the m's going to cancel, yeah. I didn't point this out a whole lot earlier, but didn't it say up here that they have an unknown mass? Did it matter though? Oh, mass canceled. So the formula that we're going to need when we finally square root both sides is that 2 times g times h, all square rooted, my velocity. And that formula is one that we kind of built ourselves. If you were to ask me, Chris, where on the data sheet is that formula? It's not. It's a formula that's only applicable in this particular scenario. So, that being said, now it's fairly easy to use the formula, though. We need 2 times gravity. Do you guys remember what g is? Okay, cool, 9.81. And then the only number that we really require is how high you were in the air. So, was it 23 something? 23.7. And there you go. That's your velocity. And I don't actually really care about the value of it. The bigger concept here is, did you follow how I solved the problem? Okay. Because we're not taking things in for marks, what I don't really care about is that everyone gets the right number at the end of the day here. I'll assume you can type numbers into your calculator at some point. But do you follow how I went through the process of determining that this energy turned into this, how these formulas kind of equaled each other right about here, how I did all the algebra? I mean, sure, we get a number when we're done, but did you follow the process? That's my big question. So, does anyone have any questions on our first starting example? Okay, let's try another one. Again, a scenario. which, by the way, is what I'm going to give you on Friday, right? So if you're kind of curious, what does Friday's performance task look like? I'm going to give you a puzzle. It's a problem to solve. Like one. That's it. And I'm going to have you try it until you get it. And I don't want to spoil the answer, right? So that's why it's one of those sort of things where it's like, if you get it, awesome, go home, enjoy your weekend. If you don't get it, keep trying until you solve the puzzle. But I don't want to give away the answer, because if I tell you the answer, then like spoils the struggle, because sometimes you have to struggle in problem solving. So, okay. New scenario. You have a slingshot. Okay. And that slingshot has a spring constant of 60 newtons per meter. If you remember what that means, it means that it takes 60 newtons of force to pull your slingshot 1 meter. Now, I highly doubt you're actually going to pull your slingshot back 1 meter. But like it would take 60 newtons to reef on it like that. Does that make sense? That's a spring constant. The variable we gave that was K, for what it's worth. And it tells you pulled it back 85 centimeters. For what it's worth, that was X in the formula. The question says, figure out the maximum height a 2.5 kilogram rock, that's a mass, could reach if you shot it straight up in the air. So in our scenario, we're going to take a slingshot, we're going to aim it straight up in the air, pull it back, and let it go phew, right off the bat. Will there be a 100% energy conversion? I even just made the sound effect. Phew. There's going to be sound, right? Which means that is there 100%? No, right? There's going to be air resistance, there's going to be friction. But what we more or less have is a scenario that looks like this. Your elastical spring energy will get converted into kinetic energy. And then that kinetic energy will get converted into gravitational energy. Gravitational energy. And let me draw a bit of a picture to help illustrate it. Here's a person apparently lying on their back to shoot a slingshot, because I can't draw a person better than that. And here is their really big slingshot in their hands. And they are going to pull back on the slingshot and launch a rock way up high in the air somehow. As the slingshot is in like the position there, at time number 1, they have energy because of a spring. Does that make sense? As soon as, watch my hands here, as soon as I let go, the spring energy starts to turn into kinetic energy. Right? And so the object at this location right here will have kinetic energy. It'll keep going up in the air until it reaches the highest it gets to, and then it's going to turn around and come back down. But for a brief split second in time, all it will have is gravitational energy, because it'll have no kinetic. Because as the object is at the very, very highest it gets to, you know how it's going to have to turn around to come back down? It'll have a velocity of 0 for a split second. So even though there are 3, like a transformation from here to here and from here to here, when I build my formula though, assuming, again, 100% efficiency, which we already know isn't even true, but assuming, right, then we maybe can make a formula that looks like this. 1/2 of kx squared should be equal to mgh. Okay. Let's just make sure you understand where that came from. This is the energy stored in the spring. And this is that energy then which allowed the rock to be way up high in the air. Right? And it really went through this process from here to get there. But now this is me building a brand new formula. It does assume that when the rock is at the highest point it can be at, it stopped. It does presume that, right? Do we know that 100% for sure? I mean, I hope so. If I shoot something straight up in the air, it should go all the way up, stop, before coming back down. If I shot it even at a bit of an angle, right? Even if I shot it at a bit of an angle, wouldn't it always be moving though? Right? So that's reading between the lines, is that by saying shooting it straight up in the air, that is an assumption we have. So, anyways, for what it's worth, then now we can try to solve this puzzle. We want to find the maximum height this rock would get to. So I've now built a formula that is logical based on what I know. Let's solve for height. How do I mathematically rearrange this for height? Okay, divide by mg. So if I divide both sides by mg, I like writing it like this for what it's worth. I would write it as kx squared over 2mg. I kind of like that. It's kind of organized. I'm just taking the 2 right here, and since it's on the denominator, I'm just throwing it down with the m's and g's. Is that okay? Okay, plug in some values. K is how stiff or stretchy the spring elastic is that I'm using, which was 60. So 60. And then I have to times by X. X is how far you pull on the spring, which was 85. But no, I'm making a mistake. What's wrong? Yeah, watch your units. This was 60 newtons for every meter, but this is 85 centimeters. So maybe make it like 0.85 and divide by 100. And then divide all that by 2 by your mass of 2.5. And multiply that by gravity, 9.81. And in theory, that should equal your height. So this time around, I'm actually going to find an answer for us just to put down a number. It's not really about getting the answer, though. It's about, do you understand the thought process of how we solved this puzzle? And more than that, do you understand that this isn't even the right answer in the first place? Like, I know we're doing all this work, but this isn't correct because we're not accounting for all of that friction, that heat, the sound. I calculated this. I got 0.88379, etc. for my height. Is that what you got to? In terms of significant digits, these numbers right here all come with 2 sig digs. So we should probably call it 0.88. And maybe a better way of putting it is, rather than saying that that's my height, maybe I should say that my height has to be less than... Did I do that right? No, that's wrong. I did that wrong. Hang on. There. Does that work? My height needs to be less than 0.88 meters. That's the highest it could possibly get to if I had no loss in energy. Right? So maybe I don't know that it went exactly 0.88, but I know that it cannot get any higher than that. Is that a fair statement to say? Right. So now the question is, if I have a way of knowing how efficient these percentages were, if I knew that, for example, I lost 1% due to heat right here, and if I knew that I lost minus 2% due to sound right here, maybe I could add to this scenario if I knew that information. But based on where we're kind of entering right here, this is about as good as we can do at this point. But the further into physics you go, the more that you can account for more and more variables. But we're a couple weeks in, right? So. How'd that work? Be able to follow. One of the things I said to the first period class is that I don't have an expectation of you guys right now that for all 4 of these examples we're going to do, I don't expect that you're going to be able to look at all 4 and go, yeah, I can do that myself. If you just are at the stage right now where you go, I know what you did, I followed every single step, that's fantastic. That's why I have a worksheet and a lab and a performance task for us to practice. Because as we get into more and more difficult questions, I don't expect that you're going to like just get them all immediately. Okay, that's not my expectation for you. Let's try another one. Here's a new scenario. Say you have a pendulum. You guys remember what a pendulum is, where it kind of swings on an arc back and forth? Say you have a 100-gram mass on a pendulum. The pendulum is on a 75 centimeter long string, and you pull it back 35 centimeters. Okay. So if I were to draw a bit of a picture, this right here could be the pendulum straight down, and the string is 75 centimeters. So far, so good. You're then going to pull the pendulum back, and so maybe the pendulum is now over here. So it's still on a 75 centimeter string, but if I were to measure how far back you pulled it, the dotted lines here, so I'll try to keep this with dotted just to keep it organized, is 35 centimeters. Everybody good with that so far? And the question is, let's find the maximum speed of the pendulum. So first physics problem solving question is, well, where will the speed be at its maximum point? Will it have its most speed when it's out here at like the edge? Yeah, it should be at the very, very bottom, because isn't it going to go no speed, speed up, slow down, speed up, slow down, speed up, slow down, as it kind of oscillates back and forth, right? Right here, your velocity will be nothing. Why will its velocity have to be nothing? Because it's turning around and going back the other way, right? And by its very nature, if you turn around and go back the opposite direction at 1 millisecond in time, you must have had no speed. Does that make sense? It's the only way to go from going north to going south. You can't just do it instantaneously. You'd have to have at least a moment where its velocity was nothing. So right here is where its velocity is going to be as its max. So why don't we consider this to be energy state number 1, and this over here to be energy state number 2. Here it has no kinetic energy. Here it has lots of kinetic energy. Now, what other energy does it have when the pendulum's been lifted up over here, though? Potential, yeah. Now, it's not. There's no springs involved, right? But at this point right here, it should have some energy due to its mass, due to its gravity, and due to its height. And I'm going to draw height with a new color here. I'll color code this. Its extra height is really about how far it is from here to here. See how it has this capacity to go yay far further down? Whatever that height is right here, that loss in height is going to cause your gravitational energy to go down, but it'll cause your kinetic energy to go up, so that at this location right here, you have some kinetic energy. So here's the good news. In terms of building our formula, it's actually the same scenario as the toboggan person. This is the toboggan at the top of the hill, and this is the toboggan at the bottom of the hill. So if you're building your own formula, you had mass, gravity, and height, and when you were done, you had some speed. You effectively changed your height for some speed. Pretty okay with that part so far? Okay, so let's rearrange for velocity. It's the same thing we did last time. You could cancel mass off of both sides. You could times both sides by 2 and square root. And as long as I'm not blitzing through the algebra too fast for you, it's the same formula we had last time. Sweet. 2 times gravity times height. Done. 2 times 9.81 times weight. How much height does it lose? Well, if I read through the stem, some kids might be like, it's 75. Well, no, 75 is how long the string is. And it's not 35, because 35 is how far back the string was pulled. We need to know how far up it is right here. And that's not any of those numbers. What do you think of them?
I don't know. I know that we have to find the distance between the line of 35 and the bottom. So we're going to have to make at least 2 triangles. The top part.
Nice.
I know what we're supposed to.
Yeah, you're starting to see the picture here, right? And this is what makes physics physics, is it's not just about plugging numbers into formulas, because here's the number we're missing. But I don't have that number, right? So, I mean, Harrison's starting to get a bit of a picture here. You used a word that I wanted to focus on. There's a triangle here. Can you guys see how there's a triangle right here? Along there. Along here. Can you guys see how there's a triangle right there? Now, again, one of the things that makes physics frustrating, but also awesome, is that I think that's about a right angle triangle. Now, do I know for sure? Do I have a protractor that I'm going to go and measure for sure? Now, that being said, that's okay. That's the beauty of physics. Is this mass right here probably exactly 100 right on the dot? Or is there a bit of wiggle room? Is this 75.0 centimeters for sure 75.0? Or could it have been 75.01? Or 74.99? Don't we already recognize that we have a little wiggle room at times? So if I were to make the assumption that it's probably a right angle, that's very reasonable. And if it's not a right angle, it's probably reasonably close to 1. Does that make sense? Okay. And that's what makes physics challenging, is that you have to kind of read between the lines sometimes, and you won't be necessarily told that explicitly. But if you can estimate that, yeah, that's probably a triangle, well, now we can bring in some skills from some other classes. One of the things you may have learned about triangles in previous classes is that if it's a right angle triangle, you can use the formula a squared plus b squared equals c squared. You guys recall that formula at all? So now using that, check this out. This side right here, 75, that would have to be c, because it's the hypotenuse, right? The longest side in your triangle, this side right here has to be the 75. Now, why don't I call this side right here a? Because it's 35. We pulled this back 35 centimeters. What I could do is I could solve right here for this side in the triangle right here. Let's call that b. Now, that's not how far this thing fell, though, right? This thing fell from here down to here. But let's talk through the process as to what that would accomplish for us. If we knew that from here to here, if we knew how far that was, isn't from here all the way down to the bottom 75? So hypothetically, let's say that B was 20. I'm just making up a number hypothetically. It's not 20, but let's say that B was 20 from right here to right here. Wouldn't that mean that from here down to here would have to be 55? Because from here to here is 20, and that's 55 more, then it adds up to 75. Do you see how, in order to solve this physics problem, we had to use some math skills otherwise? So let's solve for B, though. In order to solve for B, you'd have to, like, do 75 squared equals 35 squared plus B squared. You'd have to go B squared equals 75 squared minus 35 squared. So square root all that. Harrison, do you have an answer? I got 66.3. Is anybody else using a calculator checking this? Okay, well, I did it during the first period class. I think it was 66.3. Does everybody understand how I'm using Pythagoras' theorem to help solve this, by the way? If you'd like me to, I can explain this later one-on-one, because almost no one wants to put up their hand and say, hey, it's me, I don't get it. So I get that. If I lost you on the step, can we chat later? Because that's one of the things that's both awesome and horrible about physics, is that in order to be good at physics, you have to be able to draw on... Well, in this case here, it's Pythagoras' theorem. If you're okay with solving for that, if this B value from here to here then was actually 66.3 centimeters, then how far did this thing actually drop right here? Well, if you subtract this 66.3 from the whole thing being 75, there we go, 8.7. Yeah. And that's really what I was missing down here, is that it was 8.7. Now that was centimeters though, so I better like divide that by 100 to make it into meters, but that's how I solve the problem. And you'll notice I don't even care what the answer is right here, because that wasn't the hard part of the question. The hard part of the question was not about plugging a number into a formula. I'm going to be very, very blunt here. But if all you are capable of doing is plugging a number into a formula, you have no work skills that are useful at the next level, because we got computers that can do that for you. In the 21st century, we have computers that can do all of that stuff for us, to the point that I can ask my Google Home Mini how to do most things, right? And so if all you're basically doing is data entry, that's pretty low level. Does that make sense? But if you can solve a question like this, where you're able to use your interpretation skills, build this formula to here, and recognize how to do some extra little steps along the way, that is really what I was trying to teach you. Not the plugging numbers in a formula bit, right? Yes? From this one here to right here? I agree, but then you'd have to know how far this was from here to here, right? You could have, yeah. I could have started doing it before I began, right? And to be honest, in a real world scenario, rather than measure the pendulum at 75, and rather than measure the pendulum at 35, maybe I should have just measured this in the first place. But that's another real cool thing about physics, is sometimes you can't. Sometimes you can't measure the Earth. We're going to learn later in this course that we know the circumference of the Earth, we know the weight of the Earth. But I can't just take the Earth and put the Earth on a scale to weigh it, right? So we have to try to find a way around that. We have to find like troubleshooting methods, right? So although it would have been ridiculously easy just to measure this height using a meter stick, there was another way around it. Does that make sense? There is another. Okay. Any other questions on this particular example? Because then we'll do one more, and then I'll give you some wrap up time at the end of class here. So, anyone have questions on this one? Yeah, go for it. Well, yeah, good call here. So we really don't want to round until we're done. So you know this number right here, 66.3. I should really keep it as 63.332 and try to keep all those digits. And then when I use that number down here, I really should make it 8.7. I should make it 8.7, 8.66. Yeah. In general, you really don't want to round until you're absolutely forced to, which means like at the last step, fine, then round. I guess we have to. So, based on significant digits, this looks like we're getting 3 sig digs. So when you're done down here, make sure that it's like 1, 2, 3 digits, and that's what we're going to have to cut it off at. So, that was a good question. Let's try one more example. So this one's the pinnacle. This is about the most challenging that things can get to here. What we've got in this scenario is a pulley. Okay? And this one involves, again, a lot of that read between the lines stuff that the question is not going to specifically tell you, but we're going to have to use our our critical reasoning skills, our judgment, and be able to infer. In this scenario, there's a 12 kilogram box up in the air, and then there is a pulley going over the top, and there's kind of a counterweight on the side over here, the 750. And it says for us the 750 starts on the floor. So for what it's worth, we know that the 750 is on the floor. Sound good? I'm going to suggest a different scenario right now. Hypothetically, let's say that this rope snaps. What's going to happen to the 12 kilogram box? Well, it has a mass times the gravity times the height, and that potential energy will go down so that the kinetic energy of 1/2 mv squared will go up, and the box will eventually be in this location right here, go and smash. Right? Big old school Batman, pow, kind of things on the screen there, right? That's where the box is going to end up at eventually. Does that make sense so far? Now, that was my scenario if, for example, the rope was cut. So if this was a very simple scenario, you would just say, well, mass times gravity times height will equal 1/2 mv squared. And because of that, you'll cancel your masses. Your velocity would be equal to 2 times g times h. And hey, we've done this before, but we have a twist in this question here. The rope here didn't snap. There's a counterweight over here. So because of the counterweight, will this 12 kilogram box smash into the ground the same way it normally would? Well, no. And that's our struggle now, is how do we deal with this twist here? So let's erase what I did and maybe take stock of energy again. So let's get rid of all this. What sort of energies do we have when the 12 kilogram box is in the air and the 750 is on the ground? We have potential. Who has potential? The 12 kilogram box has potential. So we all have potential. You guys are all capable of anything you put your minds to. You all have potential. Shoot for the moon, because if you miss, you'll still be amongst the stars. That was corny. Okay. Is it okay to say, though, that like this right here is scenario 1, where this box is in the air, this box is in the air, and then if I were to maybe use a different color here, let's use blue. Should have used blue the first time. Here's scenario 2. Now the 12 kilogram box will be on the ground, and the 7.5 kilogram box will be in the air. They'll trade places. Does that make sense? Now, in terms of how far they'll travel, this is not specifically stating it, but if this box went down 3 meters, how high up did the other box go? Up 3 meters, yeah. And the question won't tell you that, but if one went down 3 meters, the other went up 3 meters. And if I were to take stock of the energy in scenario 1 versus scenario 2, in scenario 1, you have mass times gravity times height for the 12 kilogram box. Okay. The 12 kilogram box has potential energy. But is it moving yet? Not yet. Is the 7.50 kilogram box moving yet? Not yet. Is it above the ground? No. So in scenario 1, this box is really all that's providing the energy. In scenario 2, though, which is now over here, we got a few things happening. For one, the 7.5 kilogram box is in the air, which means that the 7.5 kilogram box is providing some height. And both boxes are moving. Because isn't this box moving down? And isn't this box moving up? So I could add a 1/2 mv squared for the 12 kilogram box. And I could add a 1/2 mv squared for the 7.5 kilogram box. And maybe I should label those better. Can I just call them boxes A and B? And A and B. Does that work better to maybe give them some letters to keep track of it? So if I could write this neater, maybe I'll do it down here. There's the mass of box A, gravity, and height. And after we're done the scenario, if there's a 100% energy conversion, box B is now in the air, plus box A is moving, and box B is moving. Do you see how I can't give you a specific formula to use every time? Because in this particular scenario, we've got kind of a weird twist to it. We've got gravity equaling gravity, kinetic, and more kinetic. Now, at this point here, you might be inclined to say, Chris, let's start plugging in some numbers. We know most of these values. Let's try this. Check this out. Do we not know the mass of box A? Wasn't it 12? And do we not know what gravity is? Isn't that always 9.81? That hasn't changed since the last time we checked. That is true. Which again is what I both love and hate about physics, is that this really only works if you're in the locations on Earth where gravity is 9.81. If you're on the top of a mountain, it's maybe 9.79. And if you're in the Netherlands, which is below sea level, it might actually be 9.82. Anyways, but let's assume that we're in a normal location on Earth. How much height is this box falling? 3 meters. Is that okay by that? And if I then move to this side over here, well then the 7.5 kilogram box is going to go up in the air. It's also going to undergo gravity, probably at 9.81. And reading between the lines, if one box goes down 3 meters, the other box would have to go up 3 as well, right? That hasn't changed. Over here, mass A. Isn't mass A still 12? Isn't this velocity right here, isn't this the velocity that we're solving for? Like if I go back to the question, wasn't the whole point of the question was determine the speed of the 12 kilogram box as it hits the ground? As it goes smash, we're trying to calculate this velocity right here, which means we need every other value except for this one. But man, we're off to a good start, aren't we? We know this one, we know this one, we know all these ones here. Really, the only thing we need to make sure is we know all of these. We need the mass of box B. Well, hey, that's 7.5. The only thing, that's 0.5 by the way, 7.5. The only thing we need then is the velocity of box B. But we weren't told that. So we're trying to figure out the velocity of box A as it smashes downwards. That's what we're looking for. And what we're missing is if we could know the velocity of box B as it goes upwards, that's all we're missing. Now we have everything we need to solve the problem. So what's the velocity of box B as it goes up? Here's where the reading between the lines part comes in. Aren't these two objects attached by a string? They're going the same speed. Think of a train. The lead car of the train isn't the car that's attached to it behind it going the same speed as it. It can't be going slower, otherwise the train would be separating. It can't be going faster, otherwise the train would be crashing into each other, right? By that same logic, with how this string is attached right here, whatever, it's getting to be a bit of a mess now. Let's use a new color. But whatever velocity that A is going up by, or is going down by, sorry, A is going down. Let's do it like that. A is going down. Whatever velocity A is going down by is the same velocity that B is going up by. These two velocities are the same velocity. Just one's up and one's down. How does that inferred piece of information, how does that help us solve the problem? Well, let me go back here. If we don't know this V, but we know that this V and this V are the same as each other, these two velocities are the same amount as each other. It's kind of like an algebra expression where I say that 2 equals 3 plus 4x plus 2x. If you have two variables that are the same variable that you're trying to solve for, how would you have solved this scenario right here? Yeah, you guys ever heard the phrase in math, combine like terms? Right? Well, this V right here, which I'll make in red, and this V right here, they're the same as each other. They're like terms. So in this scenario here, how did you solve it? 4x and 2x become 6x. That equals 3. That equals 2. You'd minus 3 from both sides. That's minus 1 equals 6. You guys see how you learned to solve this back in, I don't know, grade 8 or 9 algebra class? And that's what does make physics challenging, is that it's going to draw on other disciplines. But using that same logic, let's try to solve this equation up here. So I'm going to start plugging in some numbers now. We're going to get to that, yeah. Over here, we need mass times gravity times height. So I'm going to take 12 times 9.81 times 3. I'm going to get you a value. 12 times 9.81 times 3. And over here, I've got 353.16. And I'm going to actually throw joules afterwards because that's all the energy our system has. Is there more energy than that in the universe? Absolutely. But in terms of our system that we care about, that's all the energy we get to begin with. Which means that all of this energy over here better equal 353.16. Sound good? Let me move this down a little bit, though, because I think I need a bit more room. Now, some of that energy will get converted into the box that goes up in the air, which is 7.5 by 981 by 3. So 7.5 by 981 by 3 gives us 220.725 joules. So this was box A. This was box B. So far, so good? Well, the remaining energy then must be the kinetic energy of the boxes as they moved. Now, what's 1/2 times 12? Okay, so what we really have is 6v squared. And over here we need to do 7.5 cut in half, which is 3.75. So if we have 6v squared and 3.75v squared, you see how these are the two like terms? So putting them together, you actually have 9.75 v squared. And if I kind of lost you there, all I did is I took the mass and the 1/2, put them together to get the 6. The mass and the 1/2, put them together to get the 375, but I left the v. There's a v squared sitting here as a variable. Now, this value right here, why don't I subtract it to the other side? Right, so if I take 353.16 and subtract 220, 353.16 minus 220.725, I'm left with this all equaling 132.435. So box A to box B, the missing energy left over was 132 joules of energy, which must have been kinetic. Putting this over here, I've only got a few steps left. I need to take 9.75, divide both sides by 9.75. So divide by 9.75. That gives me a 13.58, etc. equals v squared. And then last thought. How do you get rid of the v squared? Okay, now I want to pause on that for a second here, though. When you square root, have you guys ever been told in the math class that there's actually a positive and a negative number? Like, what's the square root of 4? And everyone says 2, and your teacher goes, but it's also negative 2. You're all wrong, you know. Yeah, right? And 9 times out of 10, we don't care about the negative square root, but let's talk about why this makes total sense. When you square root this number, you're going to get a positive and a negative number. And the reason why you get a positive and negative number is that one of these boxes is going, and the other box is going, and that makes so much sense as to why you're getting a positive and a negative. Whatever velocity the up box is traveling, the other one's going down the same amount. So let's finish off the question here. If I square root this answer, for posterity's sake, what it's worth, it's plus or minus 3.7 meters per second. Now, what makes this question so challenging then is that half the battle here is your problem-solving skills. And problem-solving skills are tough to teach because they're non-algorithmic. Do you guys know what I mean when I use the word algorithmic? It means that, like, you always do this, then you do this, then you do this. You always follow the nice repeating process. Computers are fantastic at algorithms. They're very good at basically going do step 1, do step 2, do step 3. What makes this hard is I can't give you a set of rules to follow. In all 4 examples, there was a different twist. Hey, how's it going, buddy? That's okay. In example number 1, we started off by having gravitational before equaling kinetic afterwards.
Awesome.
I know, it is, isn't it? In scenario number 2, we had springs equaling gravitational. In scenario number 3, we were actually back to having gravitational becoming kinetic, but the challenge was we had no idea what this height amount was unless we used some math, Pythagoras' theorem. And this is a final example here. If I were to make a formula, building my formula right here, I mean, I'm not going to disagree. Like, it's getting a little messy on the board, isn't it? Right? Like, at some point, physicists are going to have, like, stuff all over the place, right? And I mean, hopefully I'll do my best to help explain where numbers came from, but building this formula right here involved potential equaling potential plus kinetic, plus you had to be able to know that these velocities were the same as each other. It doesn't tell you that. You have to figure that out on your own. So, again, this is the point where some of you are going to be like, ooh, this is fun. I like solving problems. Or you might be like, I hate this. This sucks, right? And I don't know, hopefully I can help you build those skills. But But this is where I'm going to wrap things up. It's why tomorrow I have a worksheet for you, because I've done a lot of the work today. Tomorrow I want you guys to try it. And if you get stuck, go ahead, use the answer key, right? But I'm going to challenge you, don't just go right to the answer key, right? Try, be okay with being stuck. Most of the problems that, especially in the physics world, that physicists needed to solve, they don't happen like in 10 minutes. I read a study once that said that the amount of time that the average student spends working on a math problem was 19 seconds before they give up. Now, I don't know what they're averaging, whether they're averaging like kids in grade 3 or kids in grade 12, but what I'm really going to challenge you to do, especially on Friday I'm going to give you one question to solve. It's going to involve some twists and tricks along the way that you've got to decipher through, and my challenge for you is to stick with it. Right? And some of you might get it in 5 minutes, some of you might get it in an hour. It really doesn't matter whether or not you solve it first or last. What really matters is, did you engage in the thinking needed to be able to problem solve? Because really at its core, that's what physics is. Physics is problem solving. So, okay, what questions do you have? You had your hand up. Yeah.
In this equation right now, would box B have potential energy as well?
Yeah, like that's what this one right here is. Box B has potential energy when it's up in the air, right? But it didn't have potential energy beforehand. So this is before. This was before. This was after. Does that answer your question, though? After box B did have potential energy up in the air. But it doesn't have any before because it's on the ground. And again, this is still all 100% wrong because was there 100% efficiency? There is going to be friction on this pulley right here, which then leads to people asking, like, why are we even doing this? Well, because it's the exercise of solving problems. One day we'll get rid of friction entirely. One day we'll live in the back. Well, actually, I don't want to because then I won't be able to breathe. Okay, I managed to finish a little earlier. Than my last class, so I can give you about 15 minutes now to work on 2 tasks. Can I ask you guys to challenge you to work on these 2 tasks? Here's number 1. Here were the 4 things in the reflection that I was hoping to teach you today. Hopefully you'll feel like, yes, Chris, we talked about that. Number 1, did I teach you about the different types of systems? Do you feel like you've got a good grasp of that? Most kids are pretty good at that. Do you feel like you get the idea about how conservation of energy works? It's not number 4, it's number 5. But do you feel like you get the concept behind energy is limited? Whatever we have, we have. And these last 2 are hard. I've got Physics 30 students who still struggle with this concept of building your own equation. But do you feel like you're starting to pick up the idea of like how to, depending on the scenario, make mgh equal 1/2 mv squared? Or make mgh equal 1/2 mg squared plus 1/2 mv squared plus 1/2 k, like who knows what it'll be. And then this last one right here. Do you get the idea that you're going to sometimes have to use that critical thinking, those problem-solving skills, and you may need to find information from other courses and disciplines, especially math, right? You have to have some math skills of Pythagoras' theorem and factoring and combining like terms. That'll be useful. Okay, so that's one thing I want to challenge you to try. Let me finish up here. Here's the other thing I want you to try. There are some 5 practice questions for you to make sure that you get this. Why don't we do 1 practice question together as a group, and then I'll shut up finally. So I'm going to make a YouTube video. I'm going to put the YouTube video right here at some point. I don't know why that one's not working. Okay, let's try this first question here. Theory question. Did you pick up on how the theory works? Suppose you get into an elevator and you press the downward button. At the instant the elevator is starting to move, which of these statements is true? Keep reading though, in a non-isolated system. We've been assuming isolated systems. What would happen to your mechanical energy in a non-isolated system? So let's read through these here. Did your kinetic energy go up or down? Did your potential energy go up or down? Did your mechanical energy, meaning the total sum of your system, did it go up or down? Let's do the last one first. Is it going to be mechanical energy increasing or decreasing? It has to be decreasing. Can mechanical energy ever increase? That means we'd be breaking the first law of thermodynamics. We'd be making more energy. We definitely can't have more. Can we lose, finger quotes, energy to the outside surroundings? Absolutely. And in a non-isolated system, I would expect mechanical energy to be decreasing. So it's one of these 3. Sound good? So then for the rest of it, you are in an elevator and you're about to go down. Well, were you moving? Well, were you moving? No. Now are you moving? Okay, so what's happening to your kinetic energy? Your kinetic energy must be increasing. But you are going down. So if you are physically going down, it means your potential energy must be decreasing. So I'm hoping it's this one here. Your kinetic is increasing because now you're moving. Your potential is decreasing because you're going down. And your mechanical energy should be decreasing because slowly over time you should be losing energy to friction. Yeah.
At some point, will your equals stay the same? Suspended?
That is true, yeah.
Or
Well, I mean, that's how the elevator works, is that it speeds you up, and then at some point your EQ will stay the same because you kind of go the same speed. And at some point, then it'll slow back down because they have to stop you again, right? So, okay, you have about 10 minutes left. Can I ask you guys to try those two tasks sometime in the next 10 minutes, as well as tonight, tomorrow, the next few days? And tomorrow, we're going to do a worksheet. So I'll just kind of wrap things up here. So, thanks, everybody. I hope that worked well for you. It was about an hour. That's perfect.